Hi, everyone. My name's Aline Normoyle, and I'm here with Matt Dye, and we're going to talk about our team's work to build an open source pipeline for skeletal modeling of sign language utterances from 2D video sources. So the motivation behind this work is this research question: how do human articulatory and perceptual systems shape sign languages? So we know that sign languages change over time, and there are many examples of this. So here we give one from American Sign Language. At one time, the sign for future was articulated close to the hip, and now it's articulated closer to the face. Researchers such as Frischberg and Battison have documented many of these formational changes over time. And the results of many of these changes is that we have signs that are both easier to perceive and also maybe easier to articulate as well. So in regards to the perceptual system, even before we had digital technologies for tracking eye gaze, it was well known that signers tend to look at the face. As early as 1976, Pat Sipple published an article where she discussed the impact of this viewing behavior for how the language is structured. So Sipple argued that when a sign is articulated near the face, in other words, near fixation, it was more likely that the hand shape would be important. So here's an example from American Sign Language. The sign for apple and the sign for candy are both located near the cheek. They both have a similar wrist motion, except that in apple, the index finger is bent, and in candy, the index finger is extended. So phonologically, these two signs are very similar. But of course, if you're a 7-year-old, these two signs are really different. So Sipple argued that when there were very important differences between the hand shapes, they needed to be closer to the face or closer to the point of fixation in order for them to be distinguished. If instead these signs were articulated closer to the hip, it would be harder to tell the differences between them, and they wouldn't have become attested in the language. Furthermore, considering signs that are made in our peripheral vision, it is more likely that a minimal pair located in our peripheral vision will have very different hand shapes or utilize very different kind of movement. So in this slide, we have examples for please and sorry. So both these signs are located in the same place and they have the same movement, but they have very different hand shapes. Sipple's work gives us a lot of compelling examples, but it's not based on an exhaustive survey of the ASL lexicon. So to fill this gap, Caselli and her colleagues performed a study that analyzed over 2,000 signs using the ASL-Lex dataset. So in their work, they modeled location as a function of hand shape complexity in over 2,000 signs. So their analysis supported Sipple's earlier claim: complex hand shapes are located closer to the signer's face, at least for the citation forms that are in ASL-Lex. However, we have at least two important questions that remain. So the first is, could the location of signs be influenced instead by articulatory factors rather than perceptual factors? And secondly, these analyses were done on a mature language, namely American Sign Language. Do we see the influence of these perceptual and articulatory pressures on the evolution of sign languages over time? So to study these two questions, we've been working with a data set from the Nicaraguan Sign Language Project. This project looks at several generations of signers taken over a 30-year period, and the participants in this study are all signing the same sets of stories. So this data set gives us a unique opportunity to look at our second research question: how do languages change over time? But we still have this challenge of how can we measure the articulatory effort of the signs. So to study this question, we would like to use a computer vision approach. Related work has used a computer vision approach, for example, to, as we just saw earlier in the presentation, study the relationship between sign complexity and proximity to the face. Also, researchers have studied the systematicity of gesture over generations using a computer vision approach. And also, these approaches are helping us create interesting and new data sets. However, this work is all based on a computer vision model that gives us 2D pose estimates. And so if we want to estimate the articulatory effort of different signs from our data set, we really need 3D pose estimates. And specifically, we need a 3D body that has realistic proportions. Therefore, to address this lack of good 3D pose models from video, our team has built a new software system that, one, estimates 3D poses from video, and two, fits a realistic 3D body model to those 3D poses. Here is an example from our Nicaraguan data set with the body fit. So on the left, we see the original video with our solved model superimposed on top of it. On the top right, we have the raw 3D points from the video shown as black spheres, and then our fit skeletal model shown in blue. And then on the bottom, we have a physically based representation of the same skeleton running in a physics simulator. And it's from the physically based representation that we estimate forces and energy. So let's talk about how this software pipeline works. So we call it a software pipeline because it has a series of steps that takes us from our original video to a final body model that we use for our analysis. So starting with the original video, we run our computer vision model to get 3D pose estimates. And on the right, we have a depiction of what those 3D poses look like. And we get them in image coordinates, which is independent from real-world coordinates, such as meters or centimeters. Once we have these 3D positions, we smooth the trajectories to remove jitter and noise, and then we scale them so that they more closely fit a realistic measurement. So in our software that we're showing in this presentation, we're using centimeters as our units. Once we have the 3D positions, we then fit our hierarchical skeleton to it. And so this skeleton is predefined to have realistic proportions, and then we input it to our system. And then we use a well-known algorithm called inverse kinematics to fit the poses of the skeleton so that they closely match the original 3D coordinates. So you can think of this process like the 3D coordinates are driving the motion of the body like a puppet. Once we have our skeleton, we then fit masses to it, And then we solve for velocities and accelerations. And it's these quantities that we input into our physics simulator in order to estimate metrics. And then once we have our metrics, we can then analyze them in a tool such as R. Let's look at the results again. So let's talk more about our skeletal body model. We're using a standard representation, which is a hierarchy of limbs or joints. So in this work, we're just modeling the head and the arms, and so we have the corresponding joint hierarchy here besides the image. Importantly, these limbs have fixed length, so bones can't change size, and also the limbs have constrained rotation parameters. So for example, we can specify that the joints only rotate in ways that are realistic. The most obvious example would be the elbow, which can only rotate along a single axis. We can also specify min and max joint rotations for each limb. So you might be wondering, why not analyze the 3D poses from the computer vision model directly? Well, it turns out that having a skeletal model confers several advantages. So the first is that the 3D poses that we get from our computer vision model result in limbs that are changing size. So here on the left, we have a screenshot from one of our video clips, and then on the right, we have a histogram showing the lengths of the upper arm for that same clip. And if you look here, the x-axis is the lengths of the upper arm in image coordinates. And then on the y-axis, we have the counts. But if we use a skeletal model, the upper arm length remains constant, just like we want. So the other reason to use a skeletal model is, as we mentioned before, the 3D point poses that we're getting from the model don't correspond to real-world units. They're based on the image. So a result of this is that even for the same subject across different videos, we're going to have limb sizes that differ. And to give an example, on the left here, where the participant is sitting closer to the camera, we have a larger upper arm length, which is 0.18. Whereas in a different video clip with the same subject, where she's seated a little further away, we have the upper arm length as 0.14. So by using a skeletal model that we specify a priori, we control for all these differences between videos. So to compute the articulatory effort, we're using an approach based on physical simulation. So in this type of approach, we model the limbs as rigid bodies. We also need to estimate the velocities and accelerations from the limb positions. And then we input the masses, rigid bodies for each limb, the velocities, accelerations, into our physics simulator where we estimate forces using inverse dynamics. So in this work, we're using a physics engine called DART. However, you could use different simulators as well. And in fact, we're also working with a simulator called OpenSim, which in addition to doing the rigid body simulation for estimating articulatory efforts and energy, it also allows us to model the muscles of both arms. And so we can also study the muscle activations of different signs. For example, now that we have our pipeline, we can use it to automatically annotate measures of articulatory effort, such as the energy needed to make different signs, and measures of movement, such as symmetry, onset and offset times, repetitions, production time in specified zones, and also ranges of motion. So here we can look at an example based on articulatory effort and compare the effort used to make two signs from our Nicaraguan data set. So on the left, we have the sign for binoculars, shown at half speed. And on the right, we have the sign down the stairs, also shown at half speed. So on this slide, we show plots based on our skeletal model. On the left, we have a plot showing the trajectories for the left and right wrists. And then on the right, we have a time series of the kinetic energy. So each frame of the motion, we compute the kinetic energy based on the velocities, accelerations, and masses of the limbs. And on the x-axis, we have the frame number, and on the y-axis, we have the kinetic energy on a log scale, which has units of joules. We can also look at the same plots for down the stairs. On the left, we have the trajectories of the left and right wrists, and then on the right, we have the kinetic energy, also shown on a log scale and for the same frames of motion. And here, we can directly compare the time series for both signs. So binoculars has much lower kinetic energy. It's mostly driven by the translational movement of both of the wrists. However, down the stairs has very fast angular velocity accelerations and results in much higher kinetic energy estimates. We can also use histograms to view the two kinetic energy profiles for each sign. And here it's very clear we can see that binoculars has lower kinetic energy than down the stairs, which has much higher. So although we're primarily interested in articulatory effort with this work, we can also look at many other interesting metrics using our skeletal model. So one of the metrics that we've been working with is symmetry. So here is a symmetrical sign from Nicaraguan Sign Language window. And here again, we have down the stairs. So our symmetry metric is based on measuring the similarity between the trajectories of the left and right wrists. To compute this, we first need to align the two trajectories in space so that their positions and orientations match. And then once we do that, we can compare the distances for each sample pairwise. Here's what our symmetry metric looks like for window. So on the left, we have the trajectories for both the left and right wrists. And then on the right, we have a histogram of the pairwise distances for each sample. So on the bottom, we have the distances in meters, and then on the y-axis, we have the counts. Here are the same plots for down the stairs. On the left, we have trajectories of the left and right wrists, and then on the right, we have the histogram. And you'll notice that we have both higher average pairwise distance and also a lot more variation in the distances as well. On this slide, we show a direct side-by-side comparison of the two. And here it's easy to see that window has a much smaller mean distance and also much smaller standard deviation. Some final thoughts. So this software and other tools like it have the potential to enable a new phonetics of sign language that's based on movement. Furthermore, using a skeletal model instead of analyzing the 3D points directly has several advantages for utterance analysis. First, the 3D representation that we're using is the same as with motion capture, except we're able to drive that motion without any special equipment. Also, because we're using this 3D representation, it's straightforward to integrate the results of the pipeline with other tools. So we're using the representation with various simulators, but you could also import it into renderers and other types of analysis systems. The skeletal model enforces constraints on the limb rotations and lengths. And we also are able to model rotations and not just translations. Our ongoing work. So we're in the process of analyzing our data set. We're also in the process of validating our skeletal model. So one of the challenges with this work is we don't have ground truth. However, we can still test how well our skeleton fits the original video. We can also simulate using the forces that we solve for using our system to ensure that the simulated motion matches the original motion closely. And we can also do perceptual studies to ensure that when two movements look similar in a video, we're getting similar numerical metrics as well. We're also exploring limitations with the deep learning model. We're aware that deep learning networks can have biases based on the data that's used to train it, and we're checking to ensure that it's working well for our diverse set of participants. And lastly, the system is not yet turnkey, but we'd like to eventually make it so. You have to run the computer vision model, get your intermediate 3D coordinates, then import it into our software, and then you can import the result in something like R for final analysis. So it'd be nicer if at least the video part and the body fit part could be integrated in a single software. So this work is open source, and you're welcome to try it. And the supporting tools that we're using are also open source. So here we list the resources. Feel free to reach out if you have questions or comments or problems with any of this. We're happy to talk to you and work with you. So thank you very much. Matt Dye is going to be here all week. If you have any questions or would like to talk to someone in person about this work, I'm also going to be available all week, either over Zoom or by email. And we look forward to meeting you and talking with you. Thank you very much, and we welcome questions.